Okay, so today we're going to learn about nuclear magnetic resonance or NMR. So think about atoms, that any atom that has an odd number of nucleons. Nucleons are stuff inside the nucleus. So that's like proton and neutrons together. So if it has some odd numbers of nucleons, those nucleuses are gonna spin. If it has even numbers of nucleons, like in this case, they are not gonna spin. So these guys, they do not spin. At this point, there is no NMR for these guys. They are out. So NMR works only with atoms that has a spinning nuclei. And in air level, we don't worry about any of these guys except for the proton NMR, which is this proton NMR. So we're only looking at compounds that has hydrogen. Those compounds are going to show NMR. So how this works? Basically, the idea, I'm explaining in the shortest and the briefest way possible, because then I'm going to test you on this. So the simplest explanation is, so this spinning nuclei, so the nuclei has a charge, right? It has a proton in it. So the nuclei is spinning. So it has charge and it is spinning. So it produces a magnetic field. So it has its own magnetic field. So this guy has its own magnetic field. Magnetic field. So what happens is, if you expose this guy to an external magnetic field, and then you give it some energy via, which is the radio frequency energy, if you give it some radio frequency energy, and if you keep on increasing the magnetic field strength, at some point, the nuclei is gonna flip. It's gonna, if it was opposing you, it's gonna align with the external magnetic field you have given. So think of these as bar magnets, right? So if these are bar magnets, as you know, the bar magnets point either to the north, point north and south, right? So if these nucleus are bar magnets and you are giving it an external magnetic field, so it can do two things. It can either oppose the magnetic field or it can align with the magnetic field. So the difference between the when it aligns and when it opposes can be recorded, and then you can figure out the. So this phenomenon is called resonance, right? So you can figure out that here we have a proton. So that's how it works. It's the most basic explanation. So there are two types of NMR, low resolution NMR and high resolution NMR. So at this point, I'm going to talk about low resolution NMR. So, but both of these guys are looking at protons in the compound. So they're looking at that. Okay. So in low resolution NMR, so I'm going to draw a molecule here. So let's say I have this guy. Not really good at drawing. Okay. So in this, oh no, let me make it a little bit more complex. Oh no, let's keep it that way. Okay. So in this case, so this is one proton, right? One hydrogen. So I'm just going at proton. So this is one hydrogen. So let's look at what we need to figure out is how many different proton environments are there, which basically means think of the environment as, say you're in a house, look out your window and see what kind of neighbors do you have. If you are in a place where you have exactly the same neighbors as a friend who is miles away, but he has the exactly same looking neighbors, so we can say that you guys are in the same environment. So imagine it like that. So for this hydrogen, look at its neighbors. So you have a C that has two H's and then CH2, CH3. For this hydrogen, the neighbors are the same. It is a C, two H's, and then CH2, CH3. Same case with this hydrogen. It has a C which has two hydrogens and then CH2 and CH3. So these three hydrogens are in the same environment, right? Well, what about this hydrogen? This hydrogen is bonded to a C that has two hydrogens, and that carbon is bonded to CH2, CH3. It's the same environment. So if you go on, you'll see that this guy and this guy, all of these six hydrogens are in the same environment. They're the same neighbors, same situation. But what about this guy? This guy has something different. Well, it has a C that is bonded to H, and then that C is bonded to a CH3 and a CH3. But that is similar to the case of this hydrogen, right? So the ones in the red, the hydrogens in the red are in the same environment, and the hydrogens in the green are in the same environment. So for this NMR, what I'm gonna see is, no, this shouldn't be in green. Let's ignore this. Let's make this a different color. Okay. So if I have a NMR data, so I'm gonna see a green peak. So okay, so the green peak was given by how many hydrogens? 6 hydrogens, right? So I'm gonna have a green peak that has a height of 6, just a random number. So if this is 6, the red peak is gonna have a height of 2 because because 2 hydrogens caused this peak. So if this is 6, so 1/3 of that is gonna be this. So this height is gonna be 2. So the red peak was caused by these 2 hydrogens in this environment, and the green peak was caused by all of these 6 hydrogens in the same environment. So their height is basically telling you how many hydrogens are there in that environment. So let's look at another example. So another example would be OH. Okay. So in this example, again, this hydrogen, and this hydrogen are in the same environment. This red one is in the same environment with this guy. So these two are in the same environment, but the one over here with the OH, this guy has a unique situation. There's nobody here that has the same condition as him. So he's in a different environment. So if we had an NMR peak, if we had an NMR peak for this molecule, what we're gonna see is we're gonna see a green peak that has a height of 3. So if this is, just imagine the height is 3. It's a relative height. And then we are going to have a red peak that is 2/3 of this. So this is because of 2 hydrogens. And then we're going to have one small peak here for that OH hydrogen. So that's that. So this is basically how low resolution NMR works. Low resolution NMR just tells you how many different hydrogen or proton environments are there. So we can look into this example. So in this example, so if I explode this molecule out, which means I'm going to write it out. So I have CH3, and then I have CH, Br. We don't care about Br or any other atoms. We only care about hydrogens. So this is one hydrogen, this is the other. So just bear with me. Okay. So this is a molecule. So in this molecule, I'm going to have this guy, and this guy in the same environment. These 3 hydrogens are not in the same environment as these 3 hydrogens. The reason is these guys are bonded to CBRH, whereas these 3 hydrogens are bonded to a carbon that is bonded to CH2. So these guys are different than these guys. So these 3 guys are going to be in a different environment. And then this guy is in a different environment. And these 2 are in a different environment. So I'm going to have 4 different environments for this guy. And this is interesting, right? So let's see that one. So again, I'm going to write it out. So I'm going to write it out. Okay. Oh, I think I did a mistake. So, okay. So that's that. So in this case, this hydrogen is in the same environment as this hydrogen because they have the same neighbors. Well, this hydrogen and these hydrogens are also in the same case or same environment as these two guys because they have the same neighbors. But these two hydrogens are in a different environment. So I'm going to have two peaks, right? So I'm going to have two peaks. So let me sketch these guys out. So I'm going to be a little bit more accurate this time. I'm not just going to like arbitrarily draw them. So for that, you need, on this axis, on the x-axis, there is something called chemical shift. So to figure out where they would be, where these guys would be present, you need to look at something in the data booklet, which is this. This tells you where the chemical shifts are for each guys. Say if you have an alkane, the hydrogens of an alkane would be in this area. And so on. If you have an alcohol, the OH's H is going to be here, in between 2 ppm to 4 ppm. So these units, the chemical shift is in ppm, right? And one important factor is something called TMS. So this is tetramethylsilane, so we're not going to talk about that. So it is always at 0 ppm, and the scale goes backwards. So if you see this sketch here, so this is where the TMS is. See, the TMS is at 0, and the scale is going backwards. It's increasing. It's increasing towards that. So I'm gonna cover this in more detail in the high resolution NMR, but for now we're not gonna do that. So I'm just gonna show you where. I'm just gonna sketch this one. Okay. So in this case, so I have a hydrogen that is bonded to a C, which is bonded to a halogen. So if I were to sketch the low resolution NMR plot of this, so what I'm gonna have is, let me draw the axes first. So this is the chemical shift axis in ppm. I'm going to explain what they mean in the next video, not this one. You don't need that for low resolution NMR. Okay, so I have these two hydrogens, and these two hydrogens, together they're 4 hydrogens in the same environment, and they're bonded to a carbon that is bonded to a halogen. So I'm going to go into that table, and I'm going to find a hydrogen. Look here. Look here, a hydrogen that is bonded to a carbon that is bonded to a halogen. So that guy's range is from 2 to 4 probably 4.2 ppm. So what you're gonna do is, so if this is your TMS at 0, so if this is your TMS at 0 ppm, and all the way back here is 12 ppm. So this is 12 ppm. So the green guys are going to be in the range between 2 to 4.2. So just go with 3. So this is 3, right? So the green environments, so these guys, the green ones are going to be here. So you're going to see a peak around between 2 to 4.2, which is going to have a height of 4 because this peak was caused by 4 hydrogens. And then these guys are just normal alkanes, right? These are the ones in the red. So these hydrogens are bonded to a carbon that is bonded to CH2 group, and so on. These are just normal alkanes. So I'm going to go there, and I'm going to find that here is the hydrogen that is bonded to other carbons. This is a normal alkane. Its range is from 0.2 to 1.8, I guess. So 0.2 to 1.8. So you go back, and now you want to draw the peak for the red ones. So it's, if this is 2, if this is 3, so this is 1.5. So 1.5 is good enough. So you're going to draw something that's going to be half the height. It's going to have a height of 2 because it was caused by this. So this is a proper way of sketching it.